Hello, boys and girls. Going to go through and take a look at some of these problems that we're doing for multiple choice Monday. Now, unfortunately, I can't go through and do every single problem because, well, there's 14 of them and that would take forever. So what I've decided to do is take a look at a select few of the problems that I've set up similar to problems like this, where there's free body diagrams that can be drawn, there's a lot of different forces happening, and sometimes people get a little mixed up on what they do and don't need to do. So we'll go through and do just problems like this. I'm just going to focus on the setup. If there's mathematical calculations, I'll hold off on that. I'll worry about how we can manipulate it algebraically. So for this problem here, it says a block of mass m is accelerated across a rough surface by a force of magnitude F that is exerted at an angle that's supposed to be phi, Greek letter right there, with the horizontal as shown above. The frictional force in the block exerted by the surface is magnitude lowercase f. So if we do a little free body diagram for this problem, you don't need to do a free body diagram, but it can often be very helpful in terms of setting it up. We would have a gravitational force down, normal force going up. These are not being drawn perfectly to scale. Then we have the force F going at the angle phi, and we've got frictional force. They're using little f, and it looks like this. Now, they want to know what the acceleration of the block is. And a lot of times you'd look at this and say, well, you know, I got to figure out what the net force is in the y direction and in the x direction, but you don't need to do both. For this particular problem, the acceleration is in the x direction. It's not going to be accelerating up or down. The acceleration is going towards the right. And we want to figure out just what the acceleration is in that direction. So we just need forces in the x direction, and that's it. And if need be, we would have to take a look at the answer options and say, well, how do they express things? But everything here is in terms of components of F and a force of friction. So yeah, let's go ahead and set this up. I'm going to leave the free body diagram alone, but the force F should have a horizontal and vertical component. Just to be safe, let's go ahead and write in here that X is going that way and Y is going that way. So the horizontal component, since it's adjacent to the angle phi, I'm going to say that it's F times the cosine of phi. And since this is opposite of the angle phi, it'll be F times the sine of phi. And at this point, I think I can go ahead and write out a net force equation just in the x direction. Sigma fx would equal all forces to the right, and that's just F cosine phi, minus any forces to the left, little f, should be equal to m times a. And since they want an expression for a, we can just divide by m on both sides of the equation. Sorry, I have a little bit of trouble with my pen there. It's not letting me write. So dividing both sides by m, it cancels out on the right-hand side, and we'd be left with F cosine phi, minus the force of friction divided by m. So that would be option D in this case. Now, as a mathematical problem, of course, you pop in any sort of numbers that they gave. If they were to give you a situation like this, and instead of having little f for friction, it was in terms of the weight force, well, then you would definitely want to include a vertical problem. But they don't, so let's move on. Problem number 4 on that list that I gave you. It says that a block of mass m is sliding down an inclined plane that makes an angle theta, in this case with a horizontal, as shown in the figure. The coefficient of kinetic friction between the surface and the block is just mu. Which of the following is the correct expression for the acceleration A of the block? So this is looking similar. It's same sort of setup here, except now it's in terms of on an incline. So we got to remember, if we tilt our x-axis, then we're going to have to shift a bunch of things around. But in this case, looking at the answer options, all of these are some sort of multiple of g, and they're not writing little f for friction. They're writing some mu's and things, so we're going to have to actually do both of the dimensions in this case. But at some point, you're going to just kind of memorize a little bit of it. But let's go ahead and do the full setup. If I've got my weight force going straight down towards the earth, and that's mg, and I go ahead and draw in a little y-axis going up right there, and say that this is my x-axis. I should have a normal force going in the y direction. I would have, in this case, I'm not doing a full free body diagram because I just want to kind of skip past that for this one. My MG, I make a triangle around it with the right angle opposite of my MG, which I'm going to call my hypotenuse. And due to our similar triangles, this little angle right there, this little dude right there, that is theta. And that's a memorization thing. You don't have to prove this every problem, but that's the angle theta. So the side adjacent to the angle theta would be mg cosine theta, and the side opposite would be mg sine theta. Remember, the sine component is the sliding component when you're on an incline, but only when you're on an incline. Okay, this problem, sine is not the sliding component because you're not on an incline. So in this case, I know I'm also going to have a frictional force going uphill. I'll call that F sub F. And well, here's where we can write out a net force in the horizontal direction. We know, regardless of what all the full details are, we're going to have mg times the sine of theta, trying to slide downhill, minus the force of friction, should equal m times a. And here's where you could try to cut some corners, and you could say, well, you know, if I want to go ahead and solve this, I've got, it looks like g sine theta minus friction, and well, I know friction, unless I'm mistaken, frictional force is equal to mu times the normal force. So I really got some sort of a g and a sine theta minus a mu, which has that here, just a or b. A or B seem like the only two that have a minus mu, but B is the only one that has a sine theta minus a mu. So it seems like, if I had to guess, I'd say B is the right answer without even finishing this problem. But let's go ahead and finish the problem. In the vertical direction, I don't need to write out the full solution here, but we've gone through a couple times when we looked at that F normal is going against mg cosine theta, the crushing component. So the force of friction would be mu times mg times cosine theta. And if I substitute that down below, changing my colors here, I have m times g sine theta minus mu times mg cosine theta equals m times a. Sorry, that multiplication looks like a subtraction. And at this point, the m's cancel out because every term has an m. And I'm left with acceleration is equal to g sine theta minus mu g cosine theta. And in the case of this problem, they factor out the g. So that's a lot of work. Not all these problems that are multiple choice. I mean, if you look at this problem, you're not going to look at the problem and go like, oh, I could do this in about 2 minutes. Let me add it. No, it's going to be a bit complicated. But there is this idea that the sine component's the sliding component, and friction has to have mu and something else, and the only one that really checks all those boxes just by glancing at it is B. So sometimes you might be able to make that guess, but not always. All right, we're going to make a hard jump to number 9. I'm going to pause it. All right, here we are. We magically arrived at problem number 9. Another incline problem with a free body diagram. It says a block of mass m initially moving on a rough surface inclined at angle theta above the horizontal, as shown in the figure 1. Figure 2 shows the 4 forces acting on the block. Which of the following best describes the motion of the block at the moment shown in the 2 figures? Now, I gotta be honest, I'm not sure what this little force down here is, because you don't write components of forces in a free body diagram, so it would appear that as the block's moving downhill, something is pushing downhill. Now, I apologize, this angle is clearly not the same. I don't know who drew that. This seems to represent the weight force, mg, or F sub g if you prefer to write it that way. This seems to represent the normal force, and I'm guessing since it's sliding downhill, we call this the frictional force, and then maybe this is F push. I don't know, some sort of applied force downhill. But in this case, it's clearly moving downhill, and they want us to say what's happening. Is it moving up the incline, speeding up, doing this, down, down, down? So, I mean, clearly it's moving down the incline, so A and B are off the off the table. We can't answer that. And I would also look at it and say that D can't be right, because clearly these two forces here are out of balance. There has to be an acceleration. And now the question is it speeding up as it's moving down the incline, or is it moving down the incline and slowing? So now we got to go back to that whole idea of signage. If we go ahead, or just not even necessarily signage, just direction, the direction of the velocity is downhill. And judging by these two forces right here, I would say that there's a net force uphill. So net force going uphill, which means that the acceleration is going uphill. And if my acceleration is opposite my velocity, I'm getting slow. So it is slowing down in this case. So funky diagram, but in the end, no math required. You just have to notice that there is an imbalance of force, so there is an acceleration. Okay, let's move on to number 11. So let's say hello really quickly to the sad elf boy. But number 11 here, another incline problem. God, I love these incline problems. It says a skier slides down at a constant speed down a slope, incline. Ooh, constant speed. That means acceleration equals 0. So the forces are balanced. At an angle phi to the horizontal, you figure they just pick one letter for the angle, but nope. As shown above, if air resistance is negligible, the coefficient of friction move between the skis and the snow is equal to what? Oof. This is something that you may end up memorizing, but looking at it, you can't just guess this answer. You have to actually work it out. So we'll skip some of the stuff that we would normally do, free body diagrams. We're going to say that the sliding component is the sine component of this skier's weight, the sine component going downhill, and there's going to be a friction going uphill, and those two have to balance each other out. The mg sine theta, mg sine phi, minus the force of friction has to be equal to 0 because they're going at a constant speed. There's no acceleration. So that means mg sine theta must be equal to the magnitude of the friction force. And going off of other problems, friction force is equal to mu times the normal force. Put that up here. Sorry, I can't write. And normal force in this case should just be equal to the cosine component of the weight. So I would have mg sine theta equals mu times mg cosine. I keep writing theta. It's theta, it's not phi. So in this case, if I wanted to solve for mu, the m's cancel on both sides, the g's cancel on both sides, and if I divide by cosine, I'm going to get mu equals sine theta divided by cosine theta, which, if my trig is correct, is equal to tangent, ignoring the phi. I just keep screwing up because who uses phi? Come on. Okay, so that wasn't too hard, but it's something that you might want to just lock away in your memory for a bit. Now that kind of wraps up all the problems that involve inclines on this problem set, so I think I'm going to wrap up the video there in a little less than 15 minutes.